I will.
I mean, if you gave me a spoon, I would just go like.
I will begin with a word of prayer. So, dear Father, we thank you for this day again. I thank you for this class. Just ask you to guide our steps, help us to glorify you what we do, and understand a little bit more about your creation, Lord. In your name I pray, Lord Jesus. Amen. All right, so you get started with an example here. So I think this one involves friction a little bit. So we'll see how that goes. So here we go. So two cars. Two cars of equal mass slam into each other with equal speed v0 at an intersection where perpendicular roads meet. After the collision, the cars stick together and slide a distance L until they come to rest under the force of friction. Find the coefficient of kinetic friction as a function of the given speed and the sliding distance. All right, so here's the picture. We've got car A, and we've got car B over here, right? And we're told that they have equal speed, v0, which is nice, right? They come and they collide together at the intersection where these two perpendicular roads meet, and after the collision, the cars stick together and slide a distance L until they come to rest under the force of friction. So, given the situation here, we can kind of tell what's going to happen, right? Like when they slam together, if they've got equal speed, then it's pretty intuitively clear that we're going to find motion that's at 45 degrees, right? So like, you know, and so the question then is, what's this distance L, the sliding distance? All right, so, but we don't have to assume that they go to 45 degrees. Like we can derive this using conservation of momentum. All right, now I'm not saying momentum is conserved overall because my final picture here, this is, you know, it's at rest. So momentum is not conserved in the totality of my picture. Like there's an in-between step, right? Right as they collide here, you know, at that point, momentum is conserved. And then it skids to a stop, yeah? So maybe I should add another thing to clutter my picture. Let's say that the, you know, whatever, A, B here, they stick together. And let's suppose that they have this initial velocity, we'll call it V1, all right? And so the deal is that the mass times V0, 0, plus the mass times 0 V0 is equal to twice the mass, right? Actually, was I given that these cars have equal mass? Yeah, equal mass, cars of equal mass. So two cars of equal mass, we have 2m V1, right? And so what this gives us, of course, is that V1 is what? We can divide, we get what? We get, you know, V0 over 2, V0 over 2, right? And the m's cancel. So this is the initial velocity it has as it begins to slide, right? And let's see here. What's the force of friction in the slide? We're assuming it's like, you know, a level intersection and everything. So the force of friction would simply be 2 mu m g, right? So the weight of the combined cars, you know, is 2 mg. That times mu gives me the force of friction. And the deal is the energy at 1 is equal to the energy lost, what? To friction, right? So what is the energy lost to friction overall? So E1, of course, is what? 1/2 times m plus m, that's the total mass, right? Times V1 squared. And that's going to be equal to the force of friction, which is 2 mu mg, right? Times what? Times L, right? So you're like, all that integration that we were doing, this you're finally back to just force times distance, yay. All right, so then,
Up the top for the velocity, it would be VO divided by 2. Why would it be VO multiplied by 2? You just add it together.
well, velocity is a vector.
Oh, wait, sorry.
I mean, it is true that V1 squared, I mean, you might, let me process what you're saying. V1 dot V1, that's the velocity 1 squared, right? The speed 1 squared. Which is, of course, V naught squared over 4 plus V naught squared over 4, also known as V naught squared over 2. Of course, there's a 2m on both sides. That cancels. And so I've got like 1/2 of V naught squared over 2 is equal to mu GL, I believe, which finally gives me that my coefficient of friction apparently is V naught squared divided by 4 GL. So there you go. That's the unknown here, which was the coefficient of friction. That's if the car slides, the combined car system slides the distance L, then we can infer from this that the coefficient of friction between the collided cars and the road is given by that. Up here. So V1 squared is V1 dot V1, but you know, the length of V1 is, you know, squared is this squared plus that squared, which is this plus this, but a quarter plus a quarter is a half, so yeah. Lest I forget. Here you go, I'll let you add the date. All right. My next example is a theorem. So it's more of a, it's kind of a bigger example. Here's a theorem. If two equal masses, all right, undergo a glancing elastic collision, in the plane, then afterwards they travel in perpendicular directions. So I'll work this theorem out, and it's going to be somewhat similar to the derivation we did last class for that elastic, elastic collision theorem, the one-dimensional one. This is a two-dimensional one, so it's a little bit more exciting. let me draw a picture. We're going to do that same trick we did last time. We're going to choose the frame of reference where the first mass is moving, but the second mass is at rest. So some labeling. We'll suppose that MA is equal to MB is equal to M. And we're going to choose a frame of reference in which MB is initially at rest. And we're going to let the velocity of MA point in the positive x direction. So here's a picture. Here's my MA. All right, and I'm saying it has initial velocity v naught. And we can put x coordinates in the direction of that without loss of generality here. And here's MB, all right, which is at rest in our frame of reference. Then afterwards, we have, let's say, MA going out here at velocity A, and we've got, MB going with some velocity B, all right? And so I'm going back here. This is the point of collision, all right? Like that. And so let me give some names to the angles above and below the horizontal line that cuts through the intersection point. So if I draw this horizontal line right here, let's define the angle above to be alpha and the angle below to be beta. All right. If I do that, then VA is going to be VA cos alpha, VA sine alpha, right? And VB is going to be the speed of B, cosine beta, minus the speed of B times the sine of beta, right? So now that we have set up the geometry of the problem, can you guys tell me what I should do? Like, what do we do every time? Solve? Well, yeah. That's kind of a good answer. But what law of physics are we going to use here? Oh, that's kind of cool. I don't know if I've seen that before. Some professor got like a 0000 the other day. I don't remember who it was, but. Okay, so how about this? We conserve momentum, right? So momentum conservation, it gives me what? I've got m times v naught 0. That's my initial momentum, right? What's my final momentum? The final momentum here is m times va cosine alpha, va sine alpha, plus m times what? Times vb cosine beta minus vb sine beta. So there's my momentum conservation. Of course, we can cancel out the m, right? We just divide by m, right? And so that's just momentum conservation. Let's see here if I can simplify that a little bit. We've got let's see here. So from the x component, we've got v naught equals to what? Va cos alpha plus vb cos beta, right? And from the y component, we've got 0 is equal to va sine alpha minus vb sine beta, all right? So far, everything I wrote would be true whether or not the collision was elastic, right? This equation is generally true for a collision of this nature. But it's an elastic collision, so what else do we know? So this was just conservation of momentum. Elastic means the kinetic energy before is equal to the kinetic energy after, right? So what's that look like here? We have 1/2 mv naught squared, that's my initial kinetic energy. And that's equal to what? 1/2 mva squared, right? Plus 1/2 mvb squared. So let's divide by m over 2 and get a nicer equation to play with. This tells me that v naught squared is equal to like va squared plus vb squared. All right. But we could also calculate, let's see here, what could we do? So I could chicken out, I could look at my notes, find out the solution. I'm going to try to do the algebra here so you can watch my suffering. See what happens. Give me 10 minutes. If I'm not to the end of this in 10 minutes, I will bail and go to the notes, okay? But I'm pretty sure what we do here is we square this equation, right? So v naught squared is that. If I square this equation, this gives me, VA cosine alpha plus VB cosine beta quantity squared, which by the way is VA cosine squared alpha plus 2 VA VB cos alpha cos beta plus VB squared cosine squared beta. Do you see an error in what I wrote so far? VA squared, thank you. Right, VA squared, I should have that. If you have an equation that's got velocity squared on one thing, it's got to have velocity squared on everything. Otherwise, it's dimensionally inconsistent, right? So physics is nice like that. So, all right. This gives us, apparently, that if I bring, what I'm doing next, guys, is I'm going to take, and I'm going to bring, I'm going to bring these guys, I'm going to bring those over to here. All right, in the following sense, I have VA squared times 1 minus cosine squared alpha plus VB squared times 1 minus cosine squared beta. In fact, I'll put everything on the same side. Minus 2 VA VB cos alpha cos beta. All right, equal to 0. But you guys know what what 1 minus cosine squared is what? It's sine squared. So this is actually VA squared sine squared alpha, right? Which I'm going to rewrite as VA sine alpha times VA sine alpha for some reason. And then I've got plus VB sine beta times VB sine beta, which is a weird way to write it, but I think that's going to help us. We'll see. Now, what equation have we not used yet? We haven't used the y component of momentum conservation yet, right? What does this tell us? No, it does not tell us this miserable top hat code. We'll make that go away. Stop taking up precious board space. Did I remove the camera? Okay, good. So this tells us that like VA sine alpha is actually equal to apparently VB sine beta, right? So we can trade the left-hand side for the right-hand side or vice versa, right? I can use this, let me call this equation star. we can use star to make the following modifications. I can trade this out for like VA sine alpha times VB sine beta, right? And then over here, I've got like, VB sine beta, and I can trade that for a VA sine alpha, right? In other words, I can make the first two terms the same, right? I can make those the same. And lo and behold, we have twice VA, VB, parentheses, sine alpha, sine beta, minus cos alpha, cos beta, equals to 0. This is more natural for me if I look at it instead. By the way, VA and VB are not equal to 0, right? So let's dispense with the VA, VB, right? If VA and VB are both 0, that means that the initial velocity was 0. What are we even talking about? If VA and VB are 0, who cares? So VA and VB are not 0, so I can divide by them, which means I get to myself, I get a cosine alpha, cosine beta, minus sine alpha, sine beta, equals to 0. Can you simplify this? This has appeared on tests in this course before, this problem. Not my test, but it has. Like Dr. Skambordis has asked this. Maybe I've asked this before as well. It's a pretty standard example of this whole thing. But it's hard, granted. Like it would be very unfair if I didn't show you it before I asked it of you, right? Like this would be a hard problem if I didn't show you this before I asked you of it.
We're assuming the two angles combined are broken apart at 90 degrees, correct?
No, we're trying to show that. We don't know that. We want to prove that. But that's a good question. That's the goal. Can you simplify what I have last written and I'm about to underline in green? Aren't you guys taking calculus 2? You don't need trigonometry for Calc 2? Surely you need trigonometry for Calc 2. Like what's cosine alpha, cosine beta minus sine alpha, sine beta? If I use A and B, does it make it better? What's cos A, cos B minus sine A, sine B? Cosine of what? See, this is why you guys need to know the imaginary exponentials. I'm going to take a break from physics for a second right here, because you guys don't know things that you ought to know. We'll come back to that in a second. Let me take a 3-minute detour into some mathematics that will help you remember trigonometry that you might forget. This is the imaginary exponential. The imaginary exponential is simply this. We write e to the I theta is cosine theta plus I sine theta. It turns out, and this is easy enough to remember, that if you have e to the I theta times e to the I beta, it's actually equal to e to the I theta plus beta. My argument is that you could easily remember this, right? Believe me, you could. This is cosine theta plus I sine theta. That is cosine beta plus I sine beta. Apparently, it's equal to the cosine of theta plus beta plus I times the sine of theta plus beta. I is the imaginary number. Like I times I squared is minus 1. All right? But it's really no more imaginary than the square root of 2. This is very unfortunate terminology. Complex numbers are as real numbers in the sense of philosophy. So if I multiply this out, I get myself a cosine theta, cosine beta, minus sine theta, sine beta, plus I times cosine theta, sine beta, plus cosine, excuse me, my bad, sine theta, cosine beta. In order for a complex equation to be true, it has to be the case that both the real part and the imaginary part are both equal. All right? The imaginary part being equal gives me that this sine theta plus beta has to be equal to this. So we derive the identity that sine of theta plus beta is equal to cosine theta sine beta plus sine theta cos beta. On the flip side, the real part also has to be equal. So we get that this is equal to that, which tells me that the cosine of theta plus beta is equal to cos theta cos beta minus sine theta sine beta. Now, I know you guys get a formula sheet and stuff in here, but maybe you don't in all your courses. If you ever forget the adding angles formulas for sine and cosine, you can easily derive them from this little argument. And you can do a lot more. Like, you can derive formulas for other things. Like, for example, if I wanted to know like what cosine of 3 theta times the sine of theta was, I could do this. So like cosine theta is 1/2 e to the I theta plus e to the minus I theta, and sine of theta, it turns out, is 1/2i e to the I theta minus e to the minus I theta. So if I multiply these things out, I will derive the formula for cosine 3 theta times sine theta. Now, there exists a person here who knew that identity over there before I went through all this. That's the case. I'm sure there's someone here who knows that, and you're just being polite or something. But I bet nobody here can tell me how this simplifies off the top of your head. 5 points right now. 5, 4, 3, 2. Okay, no. There we go. I didn't hear what you said. Well, I know. I regret. Okay, so we got minus 1/4i e to the 2I theta minus e to the minus 2I theta. I'm using laws of exponents. So like this times that gives me that. This times that gives me that minus. I get a minus. Minus and minus gives me that plus there. And then I've got this. This times that gives you that minus. So anyway, that is getting to the point 1/2 times the sine of 4 theta minus 1/2 times the sine of 2 theta. So there you go. I just derived a trig identity for the product of cosine and sine simply by using these formulas up there. So if you know this, and you know that, and you know that, and if you know how to do algebra of exponentials, you can derive tons of trig identities like this. Right? So anyway, let's get back to the physics. I'll make up for the mathematical digression by ending class early today. How's that sound? Okay, so then going back to my question, what's the underlined green thing? Cosine alpha plus beta equals to 0. And what is the solution of that? When is cosine 0? The input must be 90 degrees, which proves what? That alpha plus beta is 90 degrees, which is to say that they're going in perpendicular directions, as claimed, right? You can go test this out on the pool table, basically, right? If you like glancingly hit a pool ball with another ball, they should part ways about 90 degrees. So, Oh yeah, and then that's the other thing is, if this is true in one inertial frame of reference, any other constant velocity frame of reference, any other inertial frame that's related to this one, you have the same angle between these guys because they get shifted by the same shift. So the angle is maintained in the frame change of frame reference. Words. Any questions? Oh, so in my notes I say something like, if we go back and we look at problem 6.37, which is the one I did at the end of last class, there, if you look at it, we had two masses collide and they went apart. One went 30 degrees up and the other one ended up going 66 point whatever degrees down. All right? They weren't equal masses though. I asked the question, so can we judge from that that wasn't an elastic collision? And the answer is no, because that previous example, we didn't have equal masses. This equal mass part of the assumption is important. We couldn't have divided by m and did what we did without the masses being equal. So, like, I know from personal experience and many lost hours that if you try to prove this with arbitrary unequal masses, it doesn't work. And it's a path to much suffering. So, like, it has to be equal masses that the result is. So, like, if I have unequal masses and they collide in the glancing collision elastically, I have no idea what the angle is between the products. It's only for equal masses, glancing collision, we get the 90 degrees. May or may not be 90 degrees if the masses colliding are not equal. All right. So how do you discern whether or not a mass, how do you discern whether or not a collision is elastic then? The answer is to do what? Guess. How about this? We calculate the kinetic energy before the collision. We calculate the kinetic energy after the collision. And if they're equal, it's elastic. Or we made a mistake, a very fortunate mistake to prove they're elastic. But let's suppose we didn't make a mistake. If we didn't make a mistake, if they're not equal, then it was an inelastic collision. All right, so I want to enjoy some of my art with you guys, if I can find it.
It's going to be Ron Swanson throwing a cat.
Is this Ron Swanson throwing a cat?
I doubt it.
I don't think this is that. I mean, I like that, of course, but let's see here. I will find my way to it eventually. So the good news is, guys, I think we're just a touch ahead of schedule. So I'm probably going to start rotational stuff next class. Let's see here, which is good. Oh man, I will eventually find my notes. I have updated the notes, by the way, guys. I wrote about 10 pages over break on gravity. So if you look at the very end of the notes, there's more stuff there that wasn't there before. All right. Let me see if I can turn off the lights. I'll glow. Let's see here. Wait a minute, no. Let me stop that. I know where that leads to. All right, so we just went through this jibber jabber. Ooh. I believe that is a robot moose. And evil cat, of course. Goes without saying. I never know quite sure what the AI is doing. I mean, my art, I should say, but like there's just some random, I don't know. Why is there a soccer ball? I guarantee you I did not put soccer ball in the prompt. A cat riding a cat, a rocket cat. Let's see here. So two cats, so here's the deal. Two cats of equal mass are shot into the air with well, it's just fluffy. Come on, it's just fluffy. So two cats of equal mass. My art has its limits. Please, bear with me. So, two cats of equal mass are shot into the air with a speed v naught at angle theta. At the top of their flight, a bomb explodes and throws both of them forward at the same angle above the horizontal for the top cat and below the horizontal for the bottom cat. All right? So, and if you think about that, if they have equal mass, it has to be that way, because otherwise momentum couldn't be conserved before and after the collision, right? Because there's no vertical. If your cats explode at the top of the flight, right? The momentum's purely horizontal, so it has to be purely horizontal afterwards. The only way for that to be achieved, if you've got two cats exploding and flying away from each other, you must have equal vertical velocities up and down in terms of magnitude, right? Otherwise, you'd have a net vertical velocity, vertical momentum, which you didn't have before the explosion. Yeah.
I'm not saying I want it, but couldn't theoretically, instead of being up and down, it could be side to side? Adding in a third?
Well, yes, we could. I like that. What was your name again?
My name's Ryan.
I feel like you're lying, and I like it.
But like,
Could we make this problem? Well, there's a cone of possibilities. I suppose there's a cone of possibilities then. But, I mean, there's a cone of possibilities where you could have it on any two things on that cone. You know, if like the axis of the cone is the horizontal momentum, any two vectors off the cone, as long as they've got equal momentum components with respect to the like radial part of the cone, like the parts away from the axis have to cancel out. The net momentum afterwards has to still be horizontal, whether we're thinking of it as a two-dimensional horizontal or a three-dimensional horizontal, like the same story. It just makes a good bonus question.
Up and down is the same as side to side because it's a cone. It doesn't matter where it is.
Yeah, I think it wouldn't change much, really. I mean, it would change something in terms of if we think about kinematics after the point of the explosion, because of course, if you get an upward velocity, then the cat that gets blown upward is going to go further than the cat which gets blown downward, obviously, and slams into the ground faster, as you might hope. But anyway, but that's not this problem. So we, top flight of bomb explodes, and yep. Oh, that was just stretching. Cool. So the angle above the horizontal for the top cat and below the horizontal for the bottom cat has to be equal for the reasons I just explained. If the kinetic energy of the cats is increased by a factor of 4, all right, in the explosion, then find the angle of the feline motion just after the bomb. There's a problem in your homework, which is this problem, but it's not stated as this problem. This is a twist of one of your homework problems, all right? And when I put this on the test, like last year, year before, whatever it was that I did it, I did have some students get it, and I had others not, because this is kind of tricky. But it's really not that tricky. You just conserve momentum. All right, so the momentum before, I'm saying that the mass of the cat is m, so twice the mass is the total mass of the cat-cat system. All right, so m naught, v naught cosine theta, because that's the x velocity, right? If we shoot projectile motion, the cat's at angle theta with initial velocity v naught, then the x velocity is v naught cosine theta, right? So that's the initial x momentum, which is the same as the x momentum at the point of its launch from the ground, right? And then after the explosion, we've got the top cat's momentum and the bottom cat's momentum. Notice that there's a minus here, there's a plus here. It's very much like the theorem we just proved in terms of like the trigonometry of the setup, right? I could draw like the picture I have over there, you could think of those being the top and the bottom cat, right? And you could think about v naught being the x velocity of the cat-cat system beforehand if you wanted to. The picture's not quite right, but it's similar. Anyway, if you look at this, we see that you can easily see then that the top velocity has to be equal to the bottom velocity in order for this to work out to 0, right? If I have this plus that, if these have to cancel to give me back 0, it must be that Vt is equal to Vb. So we get that the speeds of the cats are equal. And As such, I also find that the final velocity is v naught times the ratio of the cosine at which the cat was launched and the angle at which it exploded off at the top of the zenith of the flight. We're also given that 4 times the initial kinetic energy is equal to the final kinetic energy. So the final kinetic energy's got 2 pieces, the upper cat and the lower cat, but it's the same kinetic energy, just, half goes up and half goes down. And then before, we have 4 times the initial kinetic energy, which remember is 1/2 the total mass, which was 2m at the start, and the initial velocity. Wait a minute. Why don't I have v naught squared here? And does that make sense? What are we told about the energy? Am I told that the energy is 4 times the initial energy, or it's 4 times the kinetic energy right from before to after the explosion? It's right from before to after the explosion, right? What's the kinetic energy right before the explosion? It is when we're at the zenith of the flight. So the speed is just v naught cosine theta, right? When the cats are being launched off the ground, they're going faster, right? But they go up, gravity slows them down at the top of the flights where the explosion happens, right? So it's already slowed down from v naught all the way down to v naught cosine theta for the speed. So that's why that's there rather than just v naught. And that gives me this, which then gives me that, which apparently, if I do algebra here and cancel the cosine squared theta and cancel the v naught squared, looks like I get cosine squared alpha is 1/4, which means that cosine of alpha is 1/2 because of the geometric origin of this term. It's got to be positive 1/2 there, since the motion's forward, as I said, thus 60 degrees. Meh? So, yep. Now, I don't think I have any homework questions on relativity and energy and momentum, but I should talk about that for you guys for a minute here. In special relativity, we learn a number of different things. One of the things we learned is that kinetic energy isn't the only kind of energy that a mass has. There's also something called rest energy. And it turns out that gamma mc squared is the sum of the rest energy and the kinetic energy. So the rest energy, mc squared, is huge. Mc squared is ginormous, right? Very, very large. On the other hand, if we look at the power series expansion of this gamma factor, this beta is the velocity over the speed of light. So as long as the speed of light is much bigger than your velocity, beta is pretty small, which means that, this is the binomial expansion. Maybe you guys remember from Calc 2, I don't know. Or if you like, this is the Maclaurin series for this function in terms of beta. The first 2 terms are this. After that, you got like higher order stuff, which is even smaller if beta is small. So gamma, to a good approximation, is 1 plus 1/2 beta squared. If you put that up into here, that gives you mc squared for this first term, and then it gives you beta squared times c squared. Well, beta squared times c squared is exactly v squared. So this, when you plug it up into there, gives you that the energy is mc squared plus 1/2 mv squared. So it gives you rest energy plus our kinetic, our classical kinetic energy, which is this equation here. I never went over here, did I? This whole time I've been. Did I ever go over to the? You moved it? Oh, thank you. When? Oh, okay, good. Thank you. Whew, that's a relief. So yeah, of course, this is Einstein's famous E equals mc squared. That's only half the story. It's actually gamma mc squared. And if you want like a quick synopsis of how special relativity works, basically you take the formulas you know and you love and you slap a gamma factor in there. This gamma is 1 when the velocity is close to 0 relative to the speed of light, and it becomes infinite as the speed approaches the speed of light. So gamma is sort of like a cosmic speed limit for your formulas. And so the kinetic energy actually, in the relativistic more correct sense, it's gamma minus 1 mc squared. Thinking of it this way becomes important if your speeds are relativistic. If your speeds are not relativistic, which they won't be in this class, then we can get away with 1/2 mv squared and we don't get into trouble. The relativistic momentum is also modified. Relativistic momentum is gamma mv, where gamma again is 1 over the square root of 1 minus v squared over c squared. And you can also look at something called form momentum, which is actually a combination of energy and momentum. We think about energy and momentum on the same footing in special relativity. In special relativity, space and time become part of a combined story, and we look at things called Lorentz transformations, which are rotations of time into space and space into time. Velocity transformations play a similar role to like rotations. Anyway, this is something, a story for a different course. I don't think I might talk a little bit more about this at the very end of the course if there's interest, but I think we have a modern physics course here where you can learn more about this there, right? And I think there's at the moment there's a week of relativity in our mechanics course that's online, but I think Dr. Budara is teaching a residential version of that course in the fall. We're going to offer a 16-week, like a regular course, right? Where you can, learn the full higher level mechanics over the course of a semester as opposed to 8 weeks. But in the 8-week course that I saw, there was like a week of relativity in there. But anyway, so I don't think I even have any homework on this. I just wanted to mention it in passing, and we'll talk more about relativity towards the end of the course. But anyway, that's it for today, guys. Let me turn that camera off before I